Bert, thank you so much for being here today. I am super excited for this conversation. You're probably a connoisseur in many topics that people don't know, but that people are excited nowadays to understand. So, super happy to have you here. And yeah, as kind of like as a tradition in this podcast, we like to know our guests from their backgrounds. What is the context that we need to know about you in order to understand who you are?
Let's start all the way from the beginning then. I'm a first generation PhD scientist in the family. I actually have a chemical engineering background. Then I didn't like the rule of thumb, so I went into get my master's and PhD and went from the engineering side all the way to effectively doing physics as a computational chemist. Came as a postdoc to the lab to Pacific Northwest National Lab in 1998. So I've been in the US and in the lab system for over 28 years. Spent my time there. I was planning to be there for a couple of years and then go back. I never left. Became a staff scientist there and eventually led some larger groups and then had an opportunity to go to Berkeley. And that's where I've been for the last 13 years.
I am a huge believer that that kind of focus and drive for work has an important why behind. Bert, why do you do all the things that you do today? What drives you?
I'm very driven by discovery and early on in my career, it was focused on, my background had been on heavy element chemistry, understanding how to handle uranium, plutonium, those kind of things. That really brought me to Pacific Northwest National Lab, which is directly next to what's called the Hanford site, a World War II site where they made a lot of uranium, plutonium that was used in the bombs that were dropped on Nagasaki and Hiroshima. So the problem they ended up with is a lot of nuclear waste. And so my background and the interest was, can we help clean that up? No, my career over time evolved. You realize that there's bigger problems. Think, can we build better batteries? Can we actually start to find ways to extract carbon from the atmosphere or from other sources so that we have less of those pollutants in the air? Being able to model those kind of things, simulate those kind of things, because that's what effectively I do. I do virtual experiments. I work very close with the experimentalists, but I do the virtual side of the experiments that they couldn't even probe. And yeah, so I started to build a lot of tools. So I've been a tool builder. I build large exascale software. Now I'm building AI tools. I build quantum tools, all with the same thing. Can I solve a scientific problem that is impacting society? And that really drives me. Can I find a better way to solve a problem? Can I find a way to build 1,000-mile battery? That's still on my list. Here in California, the idea is we are always in trouble with fresh water. Could we actually develop and that brings kind of the chemical engineering mind back too, can we actually build potentially desalination approaches and plants that are more energy neutral and cost effective? So a lot of that requires fundamental research, and that's then I build a tool so I can do the fundamental research to hopefully solve these bigger problems.
Not many people have done as much research as you've done, specifically in the sectors of what you were speaking, chemistry, physics, now AI, quantum computing. From all of those that you've done, what's one that you think is worth talking about that you might have not spoken about as much or that people might have overlooked, but that you think can have an impact on today?
I think a lot of the research that you end up doing is pieces at a time. I don't think there is one where I say that's the next Nobel Prize type thing. But I've definitely had input and ideas and gave insights in what happens with nuclear waste, which was kind of my early thing. Now, I would say the interesting problem that we have had a lot of time to try and understand is how can we capture carbon? And I think carbon is going to be our biggest problem in the near future. And that's even though my contributions are a part of a solution, as long as they are part of a solution or they provide us the insight to a solution, then I've done my job. But yeah.
Bert, you know a lot about quantum computing. Now, nowadays, a topic that has been like very hot, if I may say. A lot of money is being invested in this technology, if I might say it that way. But I think it's worth stepping back. And if you could describe us as if we were 10-year-olds, what exactly is quantum computing? How would you do that?
Well, when I talk, and I literally had to give a talk last week to people that do not have a background in quantum computing or quantum physics in general. First thing I tell them, we're surrounded by quantum already, right? So
Okay.
actually, this video call is made possible because of quantum. I would tell them about MRIs. If you've ever taken an MRI, you should be happy quantum mechanics exists because that was because of quantum mechanics. So there's a lot of things already, lights, everything that is driven by the processes of quantum mechanics. What's new, and this is what happened in the last 10, 15 years, is people realizing that they could use quantum mechanics in a different way. And one of them is quantum computing. The other ones are quantum networking for security, not to get faster than the speed of light, just safe data movement and quantum sensing. And more quantum sensors are becoming important in medical fields. But my focus has been primarily on quantum computing. Again, as I said, I build tools. And so I used to be focused on developing codes, programs, software that allowed me to use large supercomputers, exascale supercomputers. But when I came to Berkeley, I started to realize that, okay, we will have an exascale computer, which we have had now for a couple of years. But the next level up is a zeta scale computer. That would require a lot more power. And already these computers take an enormous amount of power. So that's when I started to transition and say, well, what are other computational approaches to solve my problems? This is how I got into AI. This is where the promise of quantum is. Quantum as a computer has the potential to do computations that I want to do that are larger than I could do on an exascale or bigger computer, can do it potentially faster, but also can do it more energy efficient. So if I can do it in a megawatt, which is going to take a gigawatt eventually on a classical computer, that is a win on its own because we don't have that much power. So what is unique about quantum and quantum computing? Well, then you have to go back a little bit on what it means to do anything that is in quantum information sciences. It's very disruptive. It's very different than classical computing. It effectively takes advantage of concepts in quantum mechanics, which are superposition and entanglement, with the latter being really what drives quantum computing and the power of quantum computing. So, what is superposition? The easiest way I can explain that is if you've ever flipped a coin, you know it's heads or tails once it lands on your hand. But while it's in the air, you do not know what it is. Well, that's the nice part of it because that means while it's in the air, if you do computation on it, you pretty much have all the information you can work on at the same time. So it could be either heads or tails, but you're working on everything in between. So you have a lot more information you can store in a quantum computer. It also has a side effect that you only know the outcome when you measure. And so that becomes a statistics thing. So you have to actually flip the coin many times and measure to know what the answer is going to look like. And often the answer is somewhere between heads and tails. So you have to do a lot of measurements. That changes how you actually do computation. It's not rigorous. You cannot just read out a register on a classical computer like you do on a classical computer and know what the numbers are. You need to do it many, many times.
So,
Uh,
no.
That's one concept. The other concept is entanglement, which effectively means that if you put two quantum objects very close together, they kind of become indistinguishable. And then if you separate them, they are somehow connected, which Einstein called spooky action on a distance. but it effectively means that what happens here affects what happens here. Now, that doesn't mean that you can do information exchange faster than the speed of light, because you had to move the particles apart at some point. So that only could be done at the maximum speed of light. So there's never something that is faster. But the concept that everybody still struggles with is things are connected, correlated at some way. The information that is combined here is distributed here, and neither side knows all the information. Only when you both measure them, we have all the information. And that is a concept that I think quantum physicists still struggle. But it works really good to do computations, and we can take full advantage of it. And this is where computational algorithms are getting faster and faster and solving problems that are very hard to do on classical computers.
Okay, so if I understood correctly, I'm going to rephrase to see if I got this right. So essentially, quantum computing is like supercomputing that is, I don't know, it's able to process more complex problems faster and more efficient than our normal computing would do. And it has different ways of processing that data that makes problem solving even more efficient and like far beyond what we have been solving right now. If I am
Yes, that is a good summary of the long-winded answer that I gave you.
and Bert, but there's something in my mind that I cannot kind of close, and is if these computers can compute bigger or more complex problems, then why are they more efficient in doing so? You know?
Yeah, so you have to be careful, right? So if I take a problem and run it on a classical computer, I can do it more efficiently on a quantum computer.
Mm-hmm.
If I want to take a problem that I'm working on, a chemistry, a materials problem, if I make that problem bigger, there is a very large scaling factor to that if I do this on a classical computer. That scaling factor on a quantum computer is much smaller. So let's say I want to solve a problem that would take me, well, let's say 50 or 60 qubits, which is the unit that a quantum computer is built of. 60 qubits can store what's called 2 to the n information. So 2 to 60 is actually more memory than the biggest supercomputer in the world has at this point in time. Now I can build a quantum computer that has, and we have done that in our center. We have built a quantum computer that has 256 qubits. 2 to the 256 is more than the number of particles in the universe. So there is no way that you can build a classical computer big enough to scale a problem that you can much more efficiently do on a quantum.
In the day to day, what are those problems that you are solving through quantum computing? Like if you could bring us one example.
I would say we are not there yet. Now, let me be blunt. Quantum computers are very noisy. They're very fragile. So we haven't built the systems with the accuracy yet to solve large scale problems. We're reaching there right now. Early demonstrations have shown that we can actually tackle problems that are in the chemistry, the material sciences, the high-energy physics world, that are approaching problems you couldn't do on classical computers anymore. And that's partly also because, one, the computers are noisy right now, but they're also not at the scale yet that they need to be able to run the problems, as I said, that are large that you cannot do on classical computers. We're rivaling classical computers right now. That's where we're at. And we've had early demonstrations, even in the biosphere, biomedical sphere. The Cleveland Clinic has an IBM quantum computer where they have run systems, a molecular system or a biological system that is huge. You can still do it classically, but we can do it. And that's that transition. We're now at the point where we can actually run simulations that rival classical computers. Now we all only need a quantum computer a little bit bigger, a little bit less noisy, and then the sky is the limit. So we're at that precipice. We're not over that threshold yet. And this is why you've heard and seen all those announcements of companies going IPO. They are going on the stock market and bringing in a lot of money. The latest one is Quantinium. I think probably got an IPO that values them at a couple of $1 billion. So it is that is kind of a sign that people are now realizing the world is changing. The world is reaching a point where slightly more engineering, slightly more advancements in the technology will get us to a computational platform that is going to hopefully beat the hell out of a classical computer. Now, I will say it will not beat a classical computer in everything, and that's just the nature of the beast. A quantum computer will never be good at adding 1 plus 1. That's not what it's designed for. It's for different types of problems, but those different types of problems are ubiquitous in industry. And the chemistry materials is a nice one, nice physics, but there is a lot of industry that is focused on optimizing processes, logistics, and so on. A quantum computer has been shown that they can be really good at those kind of things too. Actually doing the logistics and the routing properly in a much more efficient way than you can do on a classical computer. There is now a lot of efforts in trying to do computational fluid dynamics. So think a Boeing building its next plane. They're really now getting to a size of system that they can actually start to probe if they can actually simulate those kind of problems, those engineering problems on quantum computers. And then the biggest thing that has happened literally in the last couple of months is now that there's two entities, two companies, Google and a new startup called Atomic, that have shown that they are getting close to breaking encryption. So, Atomic showed that they can break encryption on the normal RSA and those kind of things. Google showed that they can break your crypto wallet, so that's not a good thing for a lot of people either. And that is not to show that they can do it. That's not the goal of that conversation, actually. It tells them there is an urgency to actually make the world post quantum secure. So we need to make cryptography quantum secure. And so there's a lot of things that are happening really right now. Just the last half a year has been probably the most exciting half a year in the world of quantum computing from that perspective, because the systems are getting big, we are rivaling classical, we are controlling the errors, and we are starting to demonstrate that it's going to impact society going forward. And the VC market, the stock market is responding to that. They are going public, and they're starting to build quantum computers that people need and want to use.
Do you think quantum computing could be kind of like a parallel to what AI is being nowadays, in the sense that we're moving forward with AI? AI is penetrating lots of fields, but there's a lot of discussion and also preoccupation of, if there's no security or if there's no policy around it, this is a technology that in the hands of the wrong people can go really bad. In a world, let's say we reached the world of quantum computing, and actually security was one of the topics that I really wanted to ask you about, that you slightly talk about. Do you think it could be simulated that in a moment where quantum computing is here, it's accessible and people can have it? How does that look like? And if you were, I don't know, if you could be the president of the world, what would you do in order for it to be used in a proper way? Or is it something that concerns you?
I think it's concerns the governments on their own, right? So let's say all our information that we have been encrypted pretty much is somewhere. Somebody has access to it. Our adversaries have access to anything that is encrypted right now. If they can break it with a quantum computer, they have information. Now, the good part is it's all information, right? So, a lot of ways, there is patents to be gained, but it's not that big of an issue in the long run. The real challenge is any new information, data that needs to be secured. Do we have a solution for that? Now, there is companies that have started to work and are selling products that deliver quantum keys and quantum key distribution technologies. They're out there. Banks are definitely exploring those kind of things. I think what has happened is that has been a slow progression on it. And I think the quantum computing has gone from a slow progression to a much more steeper curve and is catching up. And so what you see is definitely that countries take approaches, different types of approaches to deal with that. You see governments that are restricting through export control, restricting access outside of the country. It's not entirely clear to me if you can harness or control access just by restricting import and exports. We know if it goes for adversaries, we know China is definitely delivering quantum computers and building quantum computers at scale. We have it in Europe. We have that's the three big ones. China, the US, and Europe are the big ones that have quantum computing technologies that can reach that level. So within the US, there is a very big stance towards security and making sure they have a quantum advantage over their adversaries. I know China is doing the same thing. And China is a lot less transparent, so we don't know where they are at this point in time. We get some information, but it's hard to say. The challenge is simpler is you can have them build quantum computers that are at scale and break encryption. But the solution is to make sure that the information that you have is encoded or cryptographically protected such that it cannot be broken by. That's the real priority that I think slowly is emerging, where people are realizing that sensitive and important information needs to be quantum secure effectively, and we cannot you cannot stop the building of bigger and bigger and better quantum computers to break. Eventually, you need to find a way to make sure that the information simply is secure against the next type of technology. And by the way, it doesn't have to be quantum alone. These AI systems become so intelligent right now. Who says you couldn't break encryption with an AI system, right? So there is AI or quantum have both the potential to, and already have demonstrated on the AI side, to be very disruptive in how things operate. That also means with security of information, right? Any information you have is distributed across the world. So, and AI has picked that up. So AI can find a lot about you without actually having to decrypt the information anymore.
You were speaking about at the beginning, Bert, that lately you've been on the top front of that overlap. So, how does or is there a way to leverage AI for quantum computing?
Yeah, so I mentioned already a little bit saying PC. So a quantum computer is not good at adding one plus one. That's what a classical computer is good at. Even AI is not that good at one plus one sometimes. It's not serving that purpose. So, what I see in the future when it comes to a computing technology and a computing environment is a very strong integration of HPC, quantum, and AI. Honestly, we're all going to live in a world of agentic and agents where honestly I am asking an agent about a question or ask for a solution for something. And behind the scenes, it will either use an HPC system, it will use a quantum computer, it will use an AI system. And by the way, they all need each other. So quantum computing is very interesting, for example, because it's so noisy, there's a lot of errors. We need to decode the errors and fix the errors. For that, we rely on large HPC systems because it's very hard to do. More recently, people have relied on AI to actually figure out where the errors are in the quantum computation and fix them. So, what we already see is HPC and AI are essential to make a quantum computer operate efficiently. So, we already have AI and HPC in service of quantum. But as I said, a quantum computer is not the end solution of everything. So we also are seeing the use of quantum computers in service of HPC or AI. So we're starting to look at, can we actually do quantum machine learning? What does that mean using a quantum computer in a machine learning or an AI environment? So in the long run, it's going to be an ecosystem where we will use HPC, quantum, and AI in some way or fashion to solve a problem in service of each other, working with each other, or solving part of a problem with one to feed into another, and so on. So it's they're not going to be isolated. They'll never go and disappear. They need each other simply because the technologies are very each technology is very good at the things that they do, but they are not good at everything.
How long do you think is going to take for these technologies to be their highest point, specifically in quantum?
I would say so within the Department of Energy, Dario Gillis, the Undersecretary of the Office of Science, has made the desire clear that he would like to see quantum technology accessible by 2028 that would solve real scientific problems that you couldn't do on classical computers. If you look at the companies, their roadmaps, they have adjusted their roadmaps and believe that they can deliver on that. Based on my expertise or experience, I should say, leading one of the five NQI centers, the Quantum System Accelerator, I believe that is not an unrealistic target. So we will have by 2028 the first quantum computers that are going to exceed what you could do on a classical computer. By 2030, they will be a lot more ubiquitous and more broadly accessible. So we're talking years, not decades anymore. And that's the big transition we've seen in the last couple of years in quantum computing is that there's always it's another 10 years, another 10 years. But the curve has gone so up in the acceleration in development of error correction, scalable scaling technologies, being able to control quantum systems to a point that we're talking years to deliver these kinds of systems and be able to do computation you couldn't do classically.
Does it scare you in any sense that and it's the typical question of that we all, I think, are asking ourselves right now is where do we as humans then stand? Because these machines are going to become so powerful that actually and so automated, even more so with agentic technology, that is hard to paint where exactly humans will stand. And to that, I was reading about you and what you like, and it's like this idea of labs that can run themselves. But I think even for you, you've dedicated your life to research and to being in that lab, doing it yourself. And as I always say, I think part of that struggle, you go to the lab, you cannot solve this problem, but that struggle is exactly what leads you to waking up the next day and saying, I'm going to try again. You probably fail, you do it again and again until you get it. And that's where true satisfaction comes from. So I think you let me know. So what's your take on all
So,
of this?
yeah, so if you look at the transition of technology, so to me, quantum computing and HPC are in a little bit of a similar boat. That is just a bigger computer that I can solve bigger problems on, which is great because I'm not going in a wet lab. I'm doing virtual experiments on computers. AI is a very different beast. It has been a lot more disruptive. But the reality is, AI is here to stay. It's not perfect. It's hard to say if AI is close to actually driving discovery, or rather be a very helpful assistant in doing scientific discovery. We use it at the lab. We use AI pretty much daily. Is it to get a summary of all the information, the latest papers, so that we don't have to read every word? Or we use it to solve a problem that we have defined and say, let's explore this space. So I can go and I'm not the wet lab person, but think of a person that is in a wet lab. Okay, we have an idea that we want to solve this problem and we want to approach in these kinds of ways, and we need to do thousands of tens of thousands of experiments. We then get an answer, we get some insight, and then we have to solve our next phase of that problem that we're trying to solve. What if I can literally come up with that idea and then take a self-driving lab and run those 10,000 experiments over the weekend and look at the analysis, understand the results, and come up with the next idea after that in 3 or 4 days instead of years? That is a good thing. Sure, it changes the way I do experiments. I'm not going to be behind the bench all the time, but that doesn't change the underlying thing of what you want to do. You want to solve a scientific problem. You want to find a solution to a problem that helps society. If you do it faster because of AI, quantum, HPC, robotics, because that's an integral part of this story at that point too, that is a good thing. It gives us more time to think about the next problem we want to solve. And there is enough problems to be solved to help society. So I'm not a doomsday thinker when it comes to using all these new types of technologies to accelerate scientific discovery.
If you could have in your hands right now a perfectly running quantum computing that has all the technology, the AI integrated to solving the problems that AI is better at. You have the quantum side of it, and probably even the normal computing that we have right now. What problem would you solve?
So the one that I'm really curious, and we know we can't really model properly, we can model this piece out of a problem like this, is how does a battery and battery that we have in our car, in our electric cars, how does it really work? And where does it break down? We can understand that, we can build a better battery. That's a modeling problem that a quantum computer is going to be good at. Once we can do that modeling, we now need AI to do many of these computations and help us with the analysis of the information, because now the information we get out of a quantum computer can be used to say, we know where the defects are, we know where the challenges are, we should go into this direction to build a better battery. I honestly think there is a path to 1,000-mile battery, but we do not fully understand how batteries work. And that's very hard to model that. It's very hard to experimentally probe that. We get pieces of information. This is where quantum computer can help. This is where AI is going to help. So again, I'm not scared of all the technologies coming together. It just accelerates things. It makes it more, honestly, more exciting that we can actually really solve problems of a scale and a complexity that will help society just be more energy efficient, resource efficient, food efficient, water efficient, whatever you can think.
And why specifically this problem impacts society from a good standpoint? Like in your point of view, is it because of the carbon reduction that would bring, or batteries in general that we don't usually think about, but that they are in very specific machines that we need to do essentially everything? But in your point of view.
Think of this. Eventually, we need to get to. So I mentioned earlier a little bit about one big problem that California is having, and actually a lot of states are getting more and more into trouble around, is fresh water. If you are going to do right now, if you want to generate fresh water out of either brackish or ocean water, we need to burn an enormous amount of energy to kind of siphon off the fresh water and then leave the rest behind. It's extremely expensive. It would take enormous amounts of resources. But we could do it with solar. But of course, at night, you don't have solar, right? So if I want to have fresh water at night, I need an alternative. This is where solar energy, once harvested, could be stored in very long living, very efficient batteries, so we can do the same thing at night. So my big crazy plan is literally that. So you use solar to convert seawater into fresh water. You use technologies that are like thermoelectrics to recover the energy. You store as much as you can into batteries, and then be able to run that cycle kind of almost energy neutral. Because, yes, we burn a lot of carbon effectively to do freshwater generation right now. In Saudi Arabia, all of those countries, that's what they do. They are just using oil to boil water and generate fresh water. What's funny that people don't understand is there's a lot of resources in seawater. There's an enormous amount of lithium, which we need for batteries. There's a lot of uranium, which we could use for nuclear reactors, which is also a next generation technology that is being developed more aggressively now. There's a lot of other things there, and we want to recover that. Now you can make it even potentially more energy efficient, or sorry, resource efficient in the sense of a cost, right? If it can get a lot of materials out of seawater that we just used for fresh water, we can do cost recovery and make it maybe a very cost efficient technology. But everything in that step, better batteries, better thermoelectrics, better solar cells to recover, to capture the sun, the recovery of the minerals that are left behind, the transport of the water inland, for example. They're all computational problems, and a lot of them are fundamental science problems that you need to solve. And so this is where quantum computing, this is where AI can help. So I need all of those pieces to have my big dream of nobody having any issues with fresh water in the future.
Yeah.
And it
And
needed fresh water is needed in a lot of places where they grow our crops, so it's directly related to food. So yeah, it's an one kind of example that is always in the forefront of my mind as to how do I go from here to here and why am I working on this? Because I know what the end solution could be. There's other ones. The one big one that people always love to talk about is fertilizer. This is the famous quote as to why quantum computers are going to be big. Is it can actually model a biological system that can convert nitrogen into ammonia. It takes about 2 or 3% of the world's energy right now to do that. But the fertilizer we need for our crops. If we can do this much more energy efficient, then we can reduce the energy footprint, we can reduce the carbon footprint. So there is a lot of potentials there, but modeling that we cannot do on classical computers. So again, this is where a quantum computer can be good at. It can model these kinds of systems. We understand how it works in a biological system, and then use AI to find better solutions that mimic what nature does. Because that's what we're always doing in a lot of ways when we build anything we do is we often look after how nature has done it and then try to mimic it.
but in that process, there's a lot of discussion about this, especially here in Berkeley and in California, of how do we move to a more sustainable approach to everything that we do. And as you were speaking about your example of the fresh water, which I hope you get to crack that one. And it's when you have a problem, but this is in general in society. We as humans have been exceptionally talented to creating solutions that solve the problem of the moment. But as I've been seeing it in history, it's always like if that solution opens the door to a new problem, right? And so with everything, if you think about it, so before we didn't have cars, but now people are not walking, and so you have another problem. Or I mean, you can see it everywhere. And as you were speaking about this specific one, I was thinking, this is marvelous. Imagine having that efficiency, bringing water from the ocean and having the minerals that you were saying that can be used for other tasks. But then what about the impact in the ocean? You know what I mean? And so, and this is back to the question that I did to you, and to your point is, I think there's always going to be problems to be solved. But as a scientist that you have been doing this for your entire life, how do you see this, and how have you approached this kind of like conundrum of, okay, if I solve this one right now, it means I'm going to open another one. So where does it end, right?
That's to me, the nature of humanity, we always want to explore the next frontier. So I don't think that's against our nature. That means we are opening a new problem. So yes, and that means we have to find a new solution, a more solution. This is how we are. Why are we going into space? Because we are trying to open new frontiers, understand the next thing. Are we going to be satisfied when we go to the moon? No, we have not satisfied ourselves by going to the moon. Now we want to go to Mars, right? So we always have, as a humanity, have always driven for what's next, what is bigger, what's the next problem, what's the next interesting thing that we should be pursuing. There is people right now that are thinking about, well, human society. So humanity has been interesting because they have definitely been the big consumer of the resources of Earth. But now there is people that are thinking outside the box and say, well, there is comets, there's an Earth cloud, those kind of places. Could we actually bring one back that has enormous amounts of lithium or other minerals? There's people that are looking at the moon as a resource. This is how we are. We are always trying to find a way to use the resources and use them in the most efficient way because we know we're running out. Right? We know we're going to run out of oil and gas. That is not a secret. So we need an alternative to make sure that we still can do and have the resources we need to generate the energy we need as a society. We're learning to do it more efficiently. But this is always a problem or a next problem that we're going to solve. That's just nature. I don't think we could just sit back and say we solved all the problems. I don't know how our society would deal with that. I don't think our humanity can just sit and be.
Bert, at this point of the conversation, I like to focus on you as a guest and the experience that you've had. You've had the privilege of working in why I assume because of the way you speak about it, of your passion, probably meeting very interesting people throughout your career and throughout your life. And looking back, if you could talk to, if you want, your younger self or younger generations that are approaching what we've been speaking for the past 45 minutes, what would you tell them? Or if you could, if you had, I don't know, a son or a grandchild that is just arriving to this earth, what do you think it's fundamental for people to learn and understand to thrive in the world that we're going to live in the probably next years, as you were saying, not even decades?
It's very simple. And I've heard this, others say this too, is be curious, be inquisitive, wanna find the next thing, learn the next thing. You shouldn't be satisfied knowing what you're knowing. I can say I don't know all the things that I really want to know. I learn every day. I bring people into my world, my orbit, my work orbit that are smarter than I am because I can learn. And that's the nature you need to have. There is so much to discover. There is so much that should get you excited. Find that passion, find that direction. And again, I'm a scientist. That's my passion. But there is also people that have a very different passion. We have artists that honestly can care less about science. They have a passion to represent the world as they see it. You need passion. You need to have something that drives you. And that's what I instill in everybody that I talk to or try to talk to when they're asking those questions is be curious, be passionate, have a drive. What is it for yourself that is your mission in life? You cannot have a mission, a direction, a desire, because if you don't have a passion or a direction, you're going to stand still and society will just move past you at the speed of light. You need to have something that really makes you tick. And honestly, if you really look at humans in general, humanity in general, people always had a reason to do something. It made them tick. It gave them a drive. And it can be simple. For us, it's yeah, sure. Science is what drives me. But in less developed societies, it's finding a better way to get water, a better way to build or grow crops because it is essential for their societies. So it is very different for different people, but I believe those that have a passion to really be curious and try to make things better is is something that is going to be essential. If I have to tell that to myself, I always had that. So it's a little bit more tricky, but I still it into my nephews. I still it into my nieces. It's you need to have a drive and a passion. You have to have something that you want to help society get better.
You've, like the timings of your life, you've done the marathon type of timing, if I may say, not sprinting. You've been there, you've been developing in science, starting with chemistry, passing through physics, quantum, AI. Not many people have that resistance, if I may say it in a word. And I think personally, I feel it. We want everything now. And, I have my entrepreneurial like spirit that I think is very, very similar to a scientist. How did you push through those moments where everything seemed daunted and probably that you had to ponder your work over your other aspects of life, or that you felt kind of like defeated, but you kept on going? You've been doing this for the past decades. So how
Yeah,
did if you but that's amazing. That's amazing. I think that consistency is something to admire and replicate.
I so the reason why I do many different directions is this is the joke that I use. This is I don't like to be bored. There is
Yeah.
always new problems to be solved. So that's how I've gotten so diverse in the type of things that I do. But you know, yes, you will have setbacks, you will find challenges, you will find failures. But the cool part is that failures is actually what you learn the most of, not the success stories, the failures. And if I work on a problem and it fails, I do not get what I thought was going to happen, it often leads to the next idea that will solve that problem. So sure, there will be setbacks, but that's science for you too. It's not like an Einstein wrote his theory of relativity in one go either. He made many mistakes along the way, but every time he did, he learned something. And I think even in an entrepreneurial way, believe me, most entrepreneurs, there's a lot of them that their first company does not succeed. But the second time, they have learned of their mistakes. And that's the key part is being able to learn from your mistakes. If you look at a failure and say, well, this sucks, that's not going to help. You need to look at a failure and say, where did it go wrong? How can I use this to do that next thing better? And that's part of also being a scientist. You will always deal with failures. You'll always deal with mistakes, but you only can learn from them and be better. And so, yeah, it's not a pondering. It's just, okay, well, I have to go and switch my direction slightly to solve the problem in a slightly different way. But in core, you have certain problems you want to solve, and failure is just part of the equation.
You're, as a scientist mind, a very logical mind. How much, like, if you recounter your life, how much do you think what happened to you or what you lived was part of what you were accountable of? Or kind of like that magic, or I don't know if destiny is the word, but I'm almost 30 now. And I think about my life. There's certain things that I personally believe had to happen to me. I could not possibly not live that. There's others that were 100% in my accountability. I'm pretty curious because I think like the universe or whatever it is that rules this magical planet that we live in, and universe that we live in really has a part on. But I'm very curious to know your point. How do you see that part of life? Do you believe that there is a magic behind all of this that you've been exploring? Because You know chemistry, that is the fundamental unit of life, better than, I would say, 99 of the people out there.
Well, that's a very philosophical uh, it's there is everything happens in life is either serendipity, it's in control, but there is also a level of luck. There is also a level of you wonder, was this predestined? I don't know. I will never say that. One thing I will never say is there some higher power that drives everything? The society, our knowledge base is not big enough to give you an answer on that. Personally, as you said, I'm very logical and rational, so it does not make sense to me. But who knows, right? We do not have all the answers to all our problems, and we don't have all the solutions either. The universe is a very large place, and it's in a lot of ways, as you say, magical. In a lot of ways, quantum is still, for a lot of people, very magical. It's not fully understood. Will we ever? I'm sure we'll find a way to fully understand that. But yeah, as I said, there is still a lot of magical things that some people might look at magical. For us, means we want to understand. And that's the difference. I think in the scientific world is anything that looks odd, magical, unbelievable, we will try and find an insight that gives us a sense of why these things are happening and then find a way to use it in the future.
Hopefully, quantum can help us solve most of those mystical problems so we can replicate them
Yes.
and have, extraordinary lives. Bert, this has been an amazing conversation. Thank you so much for your time, for your knowledge. It was honestly like I have still so many questions about quantum, about all the things that this wraps around. So, I'll for sure post this episode, and we could even do a part 2 for the questions that are to come from the audience. Thank you so much for being here.
Thank you, Sophia. Appreciate the time.
I'm gonna stop.